Okay, so let's have a look at this final motivating example for discrete random variables. So we've got a number of bacterial colonies in samples of polluted water, and that has a Poisson distribution with a mean of 2 per centimetre cubed. We now take 4 1 centimetre cube samples, and they're independently sampled from this water. Find the probability at least one sample will contain one or more bacterial colonies, and how many 1 centimetre cube samples should be selected in order to have a probability of approximately 0.95 of seeing at least one bacterial colony. So this is your first, what we call a hierarchical model. And what I mean by that is we're going to have two random variables and one depends on another. So let's start, as always, by setting some notation. So first of all, we're going to let y will be the number of samples that have one or more bacterial colonies. So each of these ones, we take them and we look and say, do you have bacteria or not? And so we can say that y is going to be binomial. Each sample can be a trial, so we've got 4, and we're going to have some probability of success. Now, probability of success in this case would be we have one or more bacterial colonies when we do it, and failure would be that there's no bacteria in there. Okay, so now we need to work out what p is going to be. So let's have a new random variable called x. And x is going to be the number of bacterial colonies that we get in a sample. And what do we know? Well, each sample is 1 centimetre cubed, so x is Poisson 2. So it's sort of like y depends on a parameter p, and we get the p from another random variable x. So you've got these layers, which is why we call it a hierarchy. So first of all, what do we need? We need to work out p. So p is a success, and that's going to be the probability that we have one or more bacterial colony. So it's the probability that x is greater than or equal to 1, which is 1 minus the probability that x equals 0, which is 1 minus, we use, because it's Poisson, the probability mass function for Poisson, e to the minus 2, 2 to the 0 over 2 factorial, which is 1 minus d plus 0, 2, and when I put that in, I got 0.86. Okay, so what's the question actually ask? What's the probability that we have one or more successes? So take each sample, success or failure. We want at least one or more successes, in this case one or more samples that contain one or more bacterial colonies. Well, that's fine now. That is going to be equal to 1 minus the probability that y equals 0. Y is binomial, so that's going to be 1 minus, we've got 4, choose 0. Probability of success is 0.86, and then we get 1 minus 0.86 to the 4. And when I did that, you can check it, I got 0.9997. Okay. Now we're going to change it slightly. Instead of having a fixed n, so n is 4, we're going to say what n do we need such that the probability of picking up will be greater than or equal to 0. If you think about it, why would you care about this? Imagine that you are worried about contamination of water with bacteria. Your question might be, what's the smallest number of samples I need to do so I'll pick it up with a certain probability? So let's get ourselves a new page and have a look. So now we've got y is bin. We've got some n. And we know that our probability of success is this 0.86. That's what we calculated before. And I want the probability of y greater than or equal to 1. I'm going to put it equal to 0.95. We want it to be greater than that, but we'll calculate for equal and then think about what to do. So what does that mean? That means 1 minus, we've got n choose 0, because we don't know what n is yet, 0.86 to the 0, and 1 minus 0.86 to the n. And we want that to be equal to 0.95. Well, the good thing for us is we can rearrange that and also notice that this is just 1. This is just 1. So if I rearrange it, I get 1 minus 0.86 to the n equals 0.05. How do I solve that for n? Well, there's a couple of ways you do it, but the simplest one is you could take logs of both sides. So basically we can say the log of 1 minus 0.86 to the n equals the log of 0.05. We can, sorry, that's an n there, not a 2, I don't know why I put 2. So this we can rewrite as n log of 1 minus 0.86 equals the log of 0.05. So n equals the log 0.05 divided by the log of 1 minus 0.86. You know, say, well, which log should we use? Well, the standard log we use in statistics is log base e. It's the ln button on your calculator. Actually, in this case, it doesn't matter. As long as you use the same base for your log, so you could use log base 10 if you wanted, you would still get the same answer. You should get 1.49. That is not quite what we can't do a 1.49 sample, so we're going to round. And if you think about it, what you need to do to make sure you get at least that probability, you're going to round up. So we'll set n equal to 2. Cool. So there's your first illustration of a hierarchical model. We'll look at this a bit more in detail when we get to chapter 4, which is our bivariate distributions. Okay. Next, we're going to have a video on knife attacks in the UK and modelling that. So that's going to be a lot more R. So I'll do that next, and then we'll start chapter 3, continuous random variables. Thank you very much.